Silver bromide. Good morning, friends. Today I am going to discuss a silver bromide compound. இது வந்து AgBrனு சொல்லுவாங்க. is a soft in nature, pale yellow in color, water insoluble salt, well known for its unusual sensitivity to light. This property has allowed silver halide to become the basis of modern photographic materials. Silver bromide is widely used in photographic films and is believed by some to have been used for faking the shroud of Turin. The salt can be found naturally as the mineral bromogyrite. Preparation of silver bromide. Although the compound can be in the form of mineral form, silver bromide is typically prepared by the reaction of silver nitrate with an alkali bromide, typically potassium bromide, AgNO3, in aqueous in nature, plus KBr, potassium bromoarichrate, aqueous in nature. இது ரெண்டுத்தையும் கம்பைன் பண்ணால் நமக்கு கிடைக்கிறது வந்து சில்வர் bromide ப்ளஸ் பொட்டாசியம் நைட்ரேட். ஆல்தோ லெஸ் கன்வீனியன்ட் த சால்ட் கேன் பி சில்வர் bromide வந்து சால்ட்டு நேச்சர், பொட்டாசியம் நைட்ரேட் வந்து aqueous நேச்சர். Although less convenient, the silver bromide salt can be also prepared directly from its element. Modern preparation of a simple light sensitive surface involves forming an emulsion of silver halide crystals in a gelatin, which is then coated onto the film or other support. The crystals are formed by precipitation in a controlled environment to produce small uniform crystals, typically less than 1 micrometer in diameter and containing approximately 10 to the power of 12 Ag atoms called grains. Uniform crystals which is called as grains. The crystals are formed by precipitation in a controlled environment to produce small uniform crystals called grains, which is typically less than 1 micrometer in diameter and containing approximately 10 to 12 Ag atoms, 10 to the power of 12 Ag atoms. Reactions. Silver bromide reacts readily with liquid ammonia to generate a variety of amine complexes like AgNH3 twice Br, AgNH3 twice Br and AgNH3 twice Br2 minus. In general, AgBr plus MNH3 plus N minus 1 of Br minus gives Ag of NH3 m times Brn power 1 minus n. Silver bromide reacts with triphenyl phosphine to give a triphenyl phosphine product. Physical properties of silver bromide. Crystal structure. AgCl and AgBr all have face-centered cubic rock salt and lattice structure with the following lattice parameters. Silver halide lattice properties. Compound வந்து AgF, crystal FCC, structure rock salt NaCl, lattice வந்து A by Armstrong. AgF அது ஃபேஸ் சென்டர்டு கியூபிக் கிறிஸ்டல்னு சொல்லுவாங்க. ராக் சால்ட் ஸ்ட்ரக்சர் சோடியம் குளோரைடு. இதோட லேட்டிஸ் பாயிண்ட்டு ஏஜிஎஃபோட லேட்டிஸ் பாயிண்ட் வந்து 4.936 ஆம்ஸ்ட்ராங், ஏ பை ஆம்ஸ்ட்ராங்னு சொல்லுவாங்க. ஏஜிசிஎல் இது வந்து குளோரோ அரிக்ரைட் ஃபேஸ் சென்டர்டு கியூபிக் ராக் சால்ட்டு NaCl 5.5491. Silver bromide AgBr bromoregrite face-centered cubic crystal rock salt NaCl 5.7745. The diagram shows the unique cell structure of the face-centered cubic and rock salt structure of a rock salt structure diagram also shown here. And the larger halide ions are arranged in a cubic close packing, while the smaller silver ions fill the octahedral gaps between them, giving a 6-coordinate structure, where a silver ion Ag plus is surrounded by 6 Br minus ions and vice versa. The coordination geometry for AgBr in the NaCl structure is unexpected for AgFi, which typically forms a linear trigonal 3-coordinated Ag or trigonal 3-coordinated Ag, tetra or tetrahedral 4-coordinated Ag complexes. Unlike the other silver halides, iode aregrite AgI, அந்த AgIன்னு முன்னாடி பார்த்தோம்ல, அது iode aregriteன்னு சொல்லுவாங்க. It contains a hexagonal zincate lattice structure. இது சில்வர் bromine லுக்ஸ் லைக் திஸ். இது வந்து இது பாண்டிங் other name for silver bromide, bromoregrite, bromerite, silver bromide. CAS number is 7785231. 3D model interactive image. JSmol, ChemSpider, ECHE. Properties will be summary. Chemical formula இது வரைக்கும் பார்த்து என்ன ப்ராப்பர்ட்டிஸ் பார்த்து. Chemical formula is AgBr, molar mass 187.77 gram per molar concentration. Appearance pale yellow solid. Photosensitive, density 6.473 gram per centimeter cube solid. Melting point வந்து 432 degree Celsius. ஃபாரன்ஹீட்டில் சொல்லணுன்னா 810 டிகிரி ஃபாரன்ஹீட். கெல்வினில் சொல்லணுன்னா 705 கெல்வின். பாய்லிங் பாயிண்ட் வந்து 1502 டிகிரி செல்சியஸ், 2736 டிகிரி ஃபாரன்ஹீட், 1775 கெல்வின். டீகம்போசஸ். Solubility in water 0.140 milligram per liter per L, milligram per L. 20 degree Celsius. Solubility product KSPன்னு சொல்லுவாங்க. Solubility product வந்து 5.4 into 10 power minus 3. Solubility insoluble in alcohol, most acids, sparingly soluble in ammonia, soluble in alkali cyanide solutions. Band gap வந்து silver bromide வந்து 2.5 electron volt. Electron mobility வந்து 4000 centimeter square per volt second. Magnetic susceptibility minus 59.7 into 10 power minus 6 centimeter cube per mole. Refractive index meter D ன்னு சொல்லுவாங்க 2.253. Thermochemistry வந்து heat capacity 270 joule per kg K. STD molar entropy 107 J per mole per Kelvin. Standard enthalpy of formation minus 100 kilojoule per mole. NFPA fire diamond. Related compounds: silver fluoride, silver chloride, silver iodide. Other cations, இது சில்வர் ஃப்ளோரைட், சில்வர் குளோரைட், சில்வர் அயோடைடு வந்து ஆனியான்ஸு. கேட்டயான்ஸ் வந்து காப்பர் புரோமைடு, மெர்குரி புரோமைடு. சாலிபிலிட்டி வந்து எப்படி பண்ணுவாங்கன்னா, the silver halide have a wide range of solubilities. The solubility of a silver The solubility of silver fluoride is about 6 into 10 power 7 times that of AgL. These differences are attributed to the relative solvation enthalpies of the halide ions. The enthalpy of solvation of fluoride is anomalously large. Silver halide solubilities: silver fluoride compound which has the solubility of 172. இதோட யூனிட் வந்து கிராம் பெர் 100 கிராம் H2O. 1 கிராம் H2O, 1 கிராம் பெர் 100 கிராம் H2O. AgClோட solubility வந்து 0.00019. Silver bromide has the solubility of 0.000014. Silver iodide 0.00003. Photosensitivity: all the photographic processes have been in development since mid-18th century. There were no suitable theoretical explanations until 1938 with this publication of paper by R.W. Gurney and N.F. Mott. This paper triggered by large amount of research in fields of solid state chemistry and physics, as well as more specifically in silver halide photosensitive phenomena. Further research into mechanism revealed that the photographic properties of silver halides were a result of derivations from an ideal crystal structure. Factors such as crystal growth, impurities and surface defects, all concentrations of points, ionic defects and electronic traps which affects the sensitivity of light and allow for the formation of latent image. The major defect in silver halide is the Frenkel defect, where silver ions are located interstitially Agi plus in higher concentration with the corresponding negatively charged silver ion vacancies, that is Ag V minus. What is unique about the AgBr Frenkel pairs? Frenkel pairs is the interstitial Agi plus and exceptionally mobile, and that its concentration in the layer below the grain surface far exceeds that of intrinsic bulk. The formation energy of Frenkel pair is low at 1.16 electron volt, and the migration activation energy is unusually low at 0.05 electron volt. These low energies result in large defect concentrations which can reach near 1% near the melting point. The low activation energy in silver bromide can be attributed to the silver ion's high quadrupolar polarizability, that is, it can easily deform from a sphere into ellipsoid. The property as a result of the D9 electronic configuration of the silver ion facilitates migration in both silver ion and in silver ion vacancies, thus giving the unusually low migration energy for Ag minus V. Agv minus 0.29 to 0.33 electron volt and compared to 0.65 electron volt for NaCl. Studies have demonstrated that defect concentrations are strongly affected by crystal size, which is up to several powers of 10. Most defects such as in interstellar silver ion concentration and surface kinks are inversely proportional to crystal size, although vacancy defects are directly proportional. This phenomenon is attributed to changes in the surface chemistry equilibrium and thus affects each defect concentration differently. Impurity concentration can be controlled by crystal growth or direct addition of impurities to the crystal solutions. Although impurities in the silver bromide lattice are necessary to encourage Frankel defect formation, studies by Hamilton have shown that the specific concentration of impurities, the number of defects of interstellar silver ions and positive things reduce sharply by several orders of magnitude. After this point, only silver ion vacancy defects, which actually increases by several orders of magnitude, are prominent. Electron traps and hole traps. When a light is incident on the silver halide grain surface, a photoelectron is generated. When a halide loses its electron to the conduction band, இது வந்து கெமிக்கல் ஈக்குவேஷன் எப்படி சொல்கிறாங்கன்னா எக்ஸ் மைனஸ் ஹாலிட் அயன்ஸ், இது வந்து ஹாலிட் அயன் லாசஸ் அதை குறிக்குது, ப்ளஸ் ஹெச்மியூ தான் வந்து இது ஹெச்வின்னு போட்டிருக்காங்க. ஹெச்வி gives x plus E minus x conduction band குறிக்குது, plus E minus x வந்து halide atom. After the electron is released, it will be combined with an interstitial to create a silver metal atom. Interstitial AgI plus to create a silver metal atom AgI0. E minus plus AgI plus gives AgI0. Through the defects in the crystal, the electron is able to reduce its energy and becomes trapped in the atom. The extent of grain boundaries and defect in the crystal affect the lifetime of the photoelectron, where the crystals with a large concentration of defects will trap an electron much faster than the pure crystal. When a photoelectron is mobilized, a photohole is formed, which also needs to be neutralized. The lifetime of photohole, however, does not correlate with that of a photoelectron. The details suggest that different trapping mechanism. Malinowski suggests that the hole trap may be related to defect as a result of impurities. Once trapped, the hole attracts the mobile negatively charged defects in the lattice. The interstitial silver vacancy Agv minus H plus Agv minus reversible tends to H into Agv. இது வந்து ரிவர்சிபிள் ஆர் irreversible ரியாக்ஷனை குறிக்கும். இந்த சிம்பிள் வந்து ரிவர்சிபிள் ஆர் irreversible ரியாக்ஷன் குறிக்கும். The formation of H into Agv lowers its energy sufficiently to stabilize this complex and reduce the probability of ejection of the hole back into valency band. The equilibrium constant for hole complex in the interior of the crystal is estimated at 10 power minus 4. Additional investigations on electron and hole trapping demonstrated that impurities also can be significant trapping system. Consequently, interstitial silver ions may not be reduced. Therefore, these traps are actually loss mechanisms and are considered trapping inefficiencies. For example, atmospheric oxygen can interact with the photoelectrons to form an O2- species which can interact with a hole to reverse the complex and undergo recombination. Metal ion impurities such as copper ion and cadmium have demonstrated hole trapping in silver bromide. Crystal surface chemistry. Once the whole complexes are formed, they diffuse to the surface of the grain. As a result of this formed concentration gradient, studies demonstrated that the lifetime of holes near the surface of grain are much longer than those in the bulk, and that these holes are in equilibrium with the adsorbed bromine. The net effect is an equilibrium push at the surface to form more holes. Therefore, as the hole complexes reach the surface, they dissociate. H into AgV minus H plus AgV minus gives Br fraction Br2. By this reaction equilibrium, the whole complexes are constantly consumed at the surface, which act as a sink until removed from the crystal. The mechanism provides the counterpart to the reduction of the interstitial Agi plus to Agi0, giving an overall equation of AgBr gives Ag plus fraction Br2, latent image formation and photography. Now that some of the theory has been presented, the actual mechanism of photographic process can be discussed. To summarize, as a photographic film is subjected to an image, photon incident on the grain produces electrons which interact to yield silver metal. More photons hitting a particular grain will produce larger concentration of silver atoms containing between 5 and 50 silver atoms depending on the sensitivity of the emulsion. The film now has a concentration gradient of silver atom specks based upon varying intensity light across its area, producing an invisible latent image. While this process is occurring, bromine atoms are being produced at the surface of the crystal. To collect the bromine, a layer on the top of the emulsion called sensitizer acts as a bromine acceptor. During film development, the latent image is intensified by addition to the chemical, typically hydroquinone. The selectivity reduces those grains which contains atoms of silver. The process, which is sensitive to temperature and concentration, will completely reduce the grains to silver metal, intensifying the latent image on the order of 10 to the power of 10 and 10 to the power of 11. This step demonstrates the advantage and superiority of silver halides over other systems. Latent image, which takes only milliseconds to form and is invisible and is sufficient to produce the full image from it. After development, the film is fixed, during which the remaining silver cells are removed to prevent further reduction, leaving the negative image on the film. The agent used is sodium thiosulfate and reacts according to the following equation: AgX of S plus 2Na2S2O3 aqueous in nature, the AgX and the solid in nature, 2 compound Na2S2O3 aqueous in nature. Na3 it gives Na3AgS2O3 twice S2O3 twice AQ aqueous plus NaX aqueous in nature. an indefinite number of positive prints can be generated from the negative by passing light through it and undertaking the same steps outlined above. Semiconductor properties of silver bromide. As silver bromide is heated within 100 degrees Celsius of its melting point, an Arrhenius plot of the ionic conductivity shows the increasing value and upward turning. Other physical properties such as elastic moduli, specific heat and electronic energy gap also increases, suggesting the crystal is approaching instability. This behavior, typical of a semiconductor, is attributed to the temperature dependence of a Frenkel defect formation, and when normalized against the concentration of Frenkel defects, the Arrhenius plot linearizes.